First speaker will be Misha. Misha is another postdoc here at DLI. He previously completed his PhD at CMU, where he also was a TCS Presidential Fellow and PhD Fellow. Next year, he'll also be starting a professor at the University of Wisconsin-Madison. So without further ado, welcome, Misha.
Thank you. Yeah, thanks. Thanks everyone for coming. As mentioned, I'm a new postdoc here, so I want to start off my talk with not with the actual subject. Start working. Yeah. So I'll start off with a slide about myself and some of my research. As always, feel free to reach out to chat. I'm happy to talk about anything. Maybe I should just use the during my PhD work, most of my work was involved in discussing how do you learn across multiple tasks, where tasks can be defined as data sets, which many of you might know as the task of meta learning, so learning things like how to initialize gradient descent. It also could be algorithmic instances, so learning how to condition a linear system solver, or learning how to do bipartite matching. And lastly, learning across training runs. So training runs of neural networks and maybe how to improve hyperparameters for more maybe interestingly or more structured problem of neural architecture research, which I'll talk about today. And my research interests are in combining theory and practice, so doing things that have some theoretical or mathematical motivation or have some interesting math around them, but also have practical impacts, and integrating learning into algorithms of various kinds. Most recently, in terms of applications, I've been interested in areas in scientific computing, statistics, and language. But today, what I'm going to be focusing on is the title of the slide, or of the title of the talk, which is an investigation of specialized foundation models, I'll be abbreviating FMs. And specialized here, what I mean is foundation models beyond NLP and also beyond vision and probably beyond audio. So foundation models beyond the kind of target domains of classical AI that there's already been a lot of progress in. But before getting to those specialized foundation models, I want to go over some of my research on neural architecture research, which will connect to this investigation of specialized foundation models. And then afterwards, I want to actually do a comparison of many of these specialized foundation models that have been being released in areas like genomics or satellite imaging to traditional supervised learning. And I think this comparison is kind of very important for reasons I'll get into. And the way we'll do this comparison is to simulate the model development part of traditional supervised learning using architecture search. And we'll show that we can still beat a lot of these specialized foundation models with the kind of things that are at this point old school in vision and NLP, which is ignore the pre-training data and just use the supervised data set, and that there's, I think, a long way to go in many of these specialized domains in developing foundation models. So to get started, what is neural architecture search? The basic idea is we want to automatically develop neural architectures by setting various properties of them, such as the topology of the neural network graph, or what operations to put where in this neural network graph. So on the right is this kind of old at this point also network called Inception, which is very good in computer vision in like 2014 or so. And this was developed by teams of Google engineers. And the question of neural architecture search is, can we get away with automating all of that engineering work to design a good neural network for a specific task automatically? And this, of course, involves questions of how do you connect, how do you like route different representations across the layers of this network, and what operations do you want to put where? Do you put a conv somewhere? Which activation do you put? What are the parameters of the conv? And you might wonder, is this just hyperparameter optimization? And you would be correct. But there are interesting aspects of neural architecture search that move it beyond just regular hyperparameter optimization. First thing is that there are many more hyperparameters. Usually in hyperparameter optimization, what like the practical workflow is you tune something like momentum and the learning rate and maybe weight decay. Basically, if you're optimizer, in architecture search, you have a lot more parameters because you suddenly want to decide where to put different operations and how to connect different edges in your graph, and it becomes a lot bigger of a search space. At the same time, these hyperparameters are architectural, which means they're not part of the training routine, which allows you to actually use some efficient heuristics to do what seems like a much harder problem actually quickly. So it turns out that architecture search is actually quite efficient with the right heuristics. And the reason is that you can use the fact that these hyperparameters are architectural to do kind of hacks, basically, such as weight sharing, where instead of, ideally what you would want to do is you have your big search space and you want to try every architecture in your search space and see which one does best on some validation set. That, of course, is intractable. What weight sharing does is it combines, instead of having a discrete set of architectures, combines all the architectures into some relaxed linear or weighted combination of these architectures, trains this one big supernet combining all of these architectures, and then discretizes at the end of the training process using the validation data to kind of reveal what the kind of right architecture is to use. It's heuristic, it's a hack, it works quite well. The takeaway that you get from this is that current NOS methods, architecture search methods, are able to actually recover very good architectures for the problem at hand, often with less overhead than a single training run of a single network from scratch. Yeah.
Why do you call it weight sharing? I think of weight sharing as is weight shared across the layer, but you have actually different units.
Right. So the reason it's called weight sharing, so weight sharing usually is referred to as you reuse weights to apply to different parts of some representation. Here, weight sharing is you're sharing weights between different networks. So you're training one supernet. You're trying to figure out which operations are the right ones, but these operations are actually using the same weights to train at the same time.
Sorry, there's parallel trainings going on?
Yeah, there's one training run where you're training like, say you're at one layer of your network. You want to figure out whether you want to use 3x3 convolution or a 5x5 convolution. Instead of training two networks that have one 3x3 and one 5x5, you train one network where the 3x3 and 5x5 use the same weights, and then you do like a softmax type
That's
weighting.
not possible. They cannot use the dimensionality is different.
Well, the 5x5, you can embed the 3x3 inside the 5x5.
Oh, that's what it is.
Yeah, you can do that.
I see. So that there's a 3x3 part, and then the rest you learn.
Yeah, you can encode it. Yeah.
That's weird.
It's very weird. It's very surprising the weight sharing actually works. There are also often it does work better if you actually, they still call it weight sharing, but where you just expand the number of weights you use, so every operation gets its own weight. But so they don't actually share weights across operations, but it is one training run. And the way you actually do the training is that you assign a weight to, should at this layer, you assign like weight 0.1 to the 3x3 and 0.9 to the 5x5, and you learn that weight while training. And then at the end of this training process, you discretize to get your final answer.
So this is kind of analogous to MLEs. Does this work better than
To ML?
Like, just like mixture experts, where you also learn these gates,
I see.
some modules, have people compared.
I don't think people have compared. I think, well, weight sharing came out probably before mixture of experts, if I had to guess. Yeah, I don't think people have compared.
Yeah, interesting.
Okay, and so architecture search can be done quite efficiently using this heuristic and some others that mostly correspond to just training on less data or searching on less data. You can do architecture search very quickly, but in less cost than a single training run of regular content. Well, what is all this useful for? And this actually was a source of some controversy on, say, Twitter, where, say, a CMU professor will be like, architecture search, plus thousands of researchers, has it produced anything useful for like a concrete say layer in a neural network, right? That's what we want. And so maybe this is kind of uncharitable. There's some researcher in industry will say, sure, I don't think there's a specific layer that architecture search has produced, but state of the art on ImageNet since 2017 has been achieved using neural networks that were discovered using architecture search. I don't know if they're particularly interesting, like if the architecture search discovered any component that give us insight about what works well on a specific data set, but it is a case that state of the art on vision tests has been driven by architecture search for the past mentioned. Now, at the same time, this is still maybe not the most interesting discovery. Why should we be interested in getting state of the art on ImageNet? And over the past maybe 3 to 4 years, in some of my work back at CMU, what we've started looking at is why has all of this research been focusing on exclusively, CFAR ImageNet or the relevant kind of benchmarks in some other domains, but really it has been very much focused on natural images. When there's a whole other kind of source of data and source of machine learning tasks that has been avoided by this research, and I would argue is more interesting. And the reason it's more interesting is because the original promise of architecture search was we will discover the right architecture for your specific task, even without a bunch of Google engineers. Google engineers are focused on this natural image question. Not all of these questions are going to have thousands of engineers and billions of dollars dedicated to these specific questions. Can we do architecture search for these problems? And so we raised the question, does architecture search actually work for diverse data modalities? And we built this 10-task benchmark called NASBench 360 to find out. And NASBench 360 consisted of a bunch of different data modalities in 2D and 1D. So things like satellite imaging or genomics, PDE solving. And it also contained like one vision benchmark just to maintain some sort of backwards compatibility. And we checked for each of these, we tried some state-of-the-art architecture search methods, and we also took some networks that had been hand designed by random people working with those data sets before. And it turned out that state-of-the-art architecture search was only beating these expert design architectures on 3 out of the 10 tasks. And here, expert, I would use like loosely as people took this data set and tried a CNN and tweaked it a bit. So there wasn't like that much effort, and architecture search wasn't really doing much. Yes.
So a few things. So firstly, is this all supervised tasks?
All supervised.
Okay. And the other thing is, like no shade on academic work, but like you can't really do very large scale search in academia. So how much do you believe in freedom?
How much do I believe?
Oh wait, you're just evaluating existing methods. Or... I'm
evaluating existing expert. So, which part are you saying? So whether the experts? Yes, I don't. I think it's a bad. I don't think these are these. I don't think there was a lot of expert work done on this benchmark.
No, but the NAS methods.
Oh yes.
Where did you get those from?
We got like these were we ran them. So
so
it was
that's not very extensive.
But as I mentioned, architecture search is quite cheap. The best architecture search methods they cost less than the training run. I know it's crazy, but basically you go through a bunch of heuristics where first you do the weight sharing thing, which allows you to do everything in one run, and then you downsample your data set a lot. And it turns out that the network you discover is usually quite good. It's definitely not doing like Bayesian opt or like random search over like the full search space, but this works quite well.
This simple method.
Yeah, and this weight sharing thing was actually introduced by industry folks. Like it seems like they're interested. Yes.
Are you looking at continents specifically?
Here, yes, we were looking at continents. So we were looking at continents in the architecture search methods. Experts were allowed to design whatever. I think there was some.
And so when you say that these heuristics they work really well, you mean that in the image?
Yes. Yes.
2 questions. One, are the expert architectures working within the search space of the NAS method? So your method couldn't even have found it if that happened to be optimal.
Yeah, but I think a key component of architecture search methods, actually, as I'll kind of get into, is the search space. So you have to also be able to design a good search space so that you can search well.
And then second question, was there any intuition as to like why, like if it worked on one set of tasks, so in the iceberg thing, you segregated different types of tasks. Is there a reason to why would you expect that a general thing works in certain instances but not others? Like why would you not expect general instances?
So I wouldn't necessarily expect it, but this is kind of what architecture search is promising, right? It's either architecture search is really restricted to getting state of the art and ImageNet and other vision problems, or maybe more ambitiously, we can hope for something better, which is that we will discover some type of truly novel architectures that are interesting for specific problems. Maybe we have to go beyond cons for this and so on, but that's kind of the goal of. And people have started working on this. Is, are there more interesting operations? Can we discover the next multi-head attention?
But also compute equivalent to a single training run.
Yep. Sure, I agree, and certainly like the first method we tried, which I'll get into, was too difficult to even like run for us. Like we ran it on a few tests, it seemed to do well, but maybe I'll get into that. Right. So what's the problem with these architecture search methods? And our view of this was that all these NAS methods were designed for computer vision tasks, and classically, these vision-focused NAS methods have been aiming for a good neural network graph topology. So they had a few sets of operations, 3x3 columns, 5x5 columns, and how do you connect them in some graph? And this is probably reasonable if you want to get state-of-the-art on ImageNet, but in practice, the breakthrough architectures we've seen over the past 10 years have basically all been similar topologies built around one core operation. So, for example, in ResNet, it was ResNet you built around convolution, multi-head attention, loosely speaking, or transformers are loosely speaking ResNets with multi-head attention in them. There's recent networks for PDEs that are basically ResNets with just these specific like parameterized frequency filter layers. And so a lot of the breakthrough architectures of the last 10 years have basically not to fix the topology, something that has residual connections, and look for good operations. And so our idea was, can we design a very general search space of these search operations to encode a lot of different interesting operations beyond convolutions to do well? And we actually, I'm not going to go into details for time, but we actually came up with an expressive search space like this. And it worked well for a few totally problems, but it was far too expensive to run on, say, NAS bench speed. And after that, we did something much simpler, which we took our ResNet. ResNets consist of just 3x3 convolutions everywhere. And we basically made it efficient enough that at every layer of the ResNet, we could swap out for a more general convolution that would let us decide for us what kernel size and dilation rate to use at every layer of this ResNet. Very kind of simple. Start with 3x3 convolutions. You replace those convolutions with a better kernel size and dilation rate. And we can do this efficiently, again, in less time than it takes to run a neural network, run a single neural network, or train a single neural network. And it turns out that this beats expert architecture design on 7 out of 10 patents. So better. And it was also used in this automobile decathlon competition by the second place team. So they adapted it for their problem. So what do we have now? We have, NAS is maybe useful for getting state-of-the-art ImageNet. What I've introduced to you is a method for setting good kernel parameters in CNN. It might be useful for something. What I want to get into now is that we can actually use this first point to evaluate progress on specialized foundation mode. And I have very limited time, so I'm going to try to go through this quickly. But to introduce a problem here, I'm going to shift away also in my talk. There's been like these kind of moments in AI over the last 10 years where people have adapted to different ways of doing things. So in ImageNet, we started putting deep nets on GPUs instead of using kernel methods. In 2018 or so, people decided to put train transformers on massive corpora. And after that, nobody in NLP certainly would ever think of doing supervised learning on their task. They would always start with BERT, right? Before this, we would do supervised learning, maybe with some unsupervised word embeddings. And more recently, there was, of course, ChatGPT and context learning, but I won't get into that really. And so there's been BERT moments in NLP where people switched over from using supervised learning to using this kind of pre-trained and fine-tuned pipelines. And our question was, does this, has it happened, have these BERT moments happened in specialized domains beyond NLP and maybe beyond vision? And so to actually investigate this, we looked at 3 domains that have models that are not, they're not maybe at the scale of Llama or OpenAI models, but they are BERT scale models. So we looked at genomic sequences where there are 9 models aiming to be FMs, and some of them are decently big. We looked at satellite imaging where there are 5 such models, and time series where there are also 5 such models. And here basically, so these first 2 are basically classifications. So you want to classify some properties of the genome or of the satellite, and time series we did forecasting, kind of the core test in time series. And so what do we want to actually do here? We want to check, right, if there has been a BERT moment where people switch from what they're doing before, which is just using some supervised data and training solely on supervised data, to using these foundation models as a base and then fine-tuning, right? So we want to compare this workflow, which is have a massive corpus, you do some hyperparameter optimization of your fine-tune, and then you fine-tune on your target task. And we want to evaluate a compare this to traditional supervised learning, where you do some model development, you think about your model, you do some hyperparameter optimization, and you fine-tune, or you don't fine-tune, you train solely on the target data. And this is kind of, this whole model development part of this is kind of hard to do because we have, or at least in terms of our evaluation, because we have these 18 genomics tests, we have 8 satellite tests, we have 24 time series tests. We're not going to be able to do as like an academic lab to do an investigation of actually doing this model development for all of these things, especially since we're not doing it. And so what we came up with is kind of a natural thing of let's see if kind of a heuristic way of doing model development, which is architecture search, will get us there. And again, remember that the architecture search here we're doing is quite cheap. And so here what we're going to do, we're going to take some standard CNN, so take a residual network or take a UNet, very popular convolutional networks, and use the method we introduced before called dash to set the kernel size and dilation rates in those standards. And so what are the results? Well, for genomics and satellite imaging, we evaluated on a bunch of different tests. These are the same tests that these foundation models evaluated on, by the way. And in genomics, things seem kind of rough for foundation models. We evaluated on compared to some very big models, and in terms of average accuracy across all these tests, and we evaluated, of course, a bunch of other metrics which are very similar. It turns out that the supervised CNN is actually doing better than a lot of the foundation models.
How different are the architectures? What are you like?
So different from who?
Like from the best foundation model.
Well, the best foundation models, they're using transformers.
Right, they're not using the entire.
Yeah. So they're going to be different. They're different than say resonance. Like you do get like say interesting dilation maybe patterns, and in the past it has been shown that dilations and kernel sizes matter. Like ConvNext was developed partially by increasing the kernel size.
Right. So how much of it is because of like dash versus it's just like a CNN is just inherently better suited? Because I mean recently there have been work that show that NLPs are better suited for time series than even transformers.
Right. So I'll get to time series. Okay. Time series, you're onto something, I guess. But genomics, just a regular wide resonant will not do this well.
Okay.
You should just
Sure, I'm almost. And then for satellite imaging, we do kind of in between the best and the second best foundation model. There are 5 of them. I guess the hope for something like a BERT moment would be that like these foundation models are actually doing better than just training directly in target data without using training data. And the last domain we looked at was time series. And here actually the dash kind of workflow that we introduced did not work well. Here the news actually is a lot worse for time series, which is that we took an AR model, which has 513 parameters. There's no typo here. And it does better than a lot of these foundation models. It doesn't do better than all of them, but it does between the best and second. And it's not that far away from the best. And this is not great. I don't know what to say. There's part of this where like the kind of time series, like they're maybe not doing full fine tuning. Some of them are doing linear programming. There's a lot of interest in these at times of doing like zero-shot performance. And so maybe they're not focused on just this thing, but some of them are actually doing fine tuning and claiming that we're great. But none of them, for some reason, they all compare to each other. They don't compare to this century-old AR model. I don't know. But this is what we trained and it works. So that's the results. Yeah, takeaways. I think we, in a lot of specialized domains, we actually haven't gotten our BERT moment. We haven't suppressed supervised learning. And that's important compared to FMC development. These specialized domains, too strong, well-tuned, and domain-specific. In the case of, say, AR, baseline. And I think there are directions here. We should do better modeling. We should get better data sources for these specialized domains. We might be able to apply language models in a cross-modal fashion, as we've done in some past work. But yeah, I'll finish. So thank you.